Hello and welcome to Section 3.1 on derivatives and rates of change. Since Section 2.2, we've been focused on limits, what they are, how to compute them, and how they are used to define continuity. Though we will turn our attention to other topics, nearly every topic we discuss in the calculus sequence will be an application of limits. After all, calculus is the study of change, and the limit is how math describes the basics of change. The remainder of the semester, we will be focused on derivatives and integrals, with a much greater focus on derivatives. Derivatives come directly from tangent lines. Recall in Section 2.1 that a secant line of a curve f is a line that crosses the curve at 2 points. The slope of a secant line is given by the formula f of b minus f of a, the rise, over b minus a, the run. In Section 2.1, we define the tangent line to a curve f as the secant line of 2 points separated by an infinitesimally small distance. Now that we understand limits, we can describe the tangent line at the point P as the limit of secant lines through P and a point Q on the curve where Q approaches P. A tangent line is a line, and the equation of a line can be found with a point on the line and the slope of the line. As a tangent line always includes the point P, we can give most of an equation describing the line. We only lack the slope of the tangent line. Since the tangent line is the limit of secant lines, the slope of the tangent line is the limit of the slope of the secant lines. That is, the limit of the difference quotient as b approaches a. When you calculate the derivative of f at the x value a, you find the slope of the tangent line at a. The derivative is the limit of the slope of the secant line between a and b as we let b approach a. An alternative way to view the derivatives is that it's the slope of secant lines between two lines that are h distance apart, say the point at a and the point at a plus h, as the difference h shrinks to 0. Notice that the definition of the derivatives are equivalent. If we substitute in the first, letting b equals a plus h, we find that the difference quotient can be altered to that of the second derivative. We are taking the limit as b approaches a, and this tells us what h is approaching. It is approaching 0 as the difference between b and a is approaching 0. The definitions of the derivative are equivalent, and you can use whichever you like, though we strongly recommend that you learn both. We now have many terms that are related to two concepts: average and instantaneous rate of change. An average rate of change, such as the average velocity of an object, how fast an object is moving on average over a length of time, is found with two distinct points on a function. It is the slope of a secant line. An instantaneous rate of change, such as the instantaneous velocity of an object, how fast an object is moving at a particular instant in time, is found using a single point and is the derivative, the slope of the tangent line. The slope of a line is a rate of change. It measures the rate of change in one variable in relation to the rate of change in the other. A derivative involves the limit, and we have seen in other sections that limits can fail to exist. When a derivative exists at a point, we say that the function is differentiable at that point. There are many ways that a point can fail to be differentiable, but the quickest way for a function to be non-differentiable is to have no actual value f of a. Note that the definition of the derivative explicitly calls for the actual value f of a. As mentioned earlier, derivatives are limits, and as we have seen, limits do not always exist. There are three scenarios in which the function can fail to be differentiable at a point. On locations on the graph that appear to be corner-like or cusp-like, the derivative is not differentiable. The appearance of a cusp or corner is due to the slope from the left being unequal to the slope from the right. Therefore, the two-sided limit, the derivative, fails to exist. A vertical tangent line occurs when a function increases or decreases incredibly fast. The limit of the slope of the secant lines from either the left or the right is infinite. So the derivative, the limits of the slopes, does not exist. At discontinuities, a function fails to be differentiable. In fact, if a function is differentiable at a point, then it must be continuous at that point. We will take a much closer look at cusps, corners, vertical tangents, and discontinuities in class. When a function is differentiable at a point P, the derivative of the function at P must exist. We gain information about the function at the point P that we will use in chapters 3 and 4. The major applications of the derivative will be in estimating values and differences, section 4.1, sketching curves, section 4.4, relating rates of change through equations, that'll be in section 3.10, and finding optimal solutions to word problems. In Chapter 3, we spend time to develop rules to quickly calculate derivatives without appealing to the definition and the limit. Our first techniques will be introduced in Section 3.2. You've seen the basics. Now work towards mastery through practice and study.